Okay. The next student talk we have is from Namasivayam. Namasivayam. Hi, Namasivayam. Hi, everyone. So we have Namasivayam joining us for the talk today. He's a PhD candidate at IIT Delhi. He is advised by Professor Rohan Paul and Professor Parag Singla. His research is basically in neuro-symbolic AI for embodied intelligence, spanning robot manipulation, verifiable and trustworthy robotics, and human-centric decision making. And he's also a recipient of Google PhD fellowship. And we'll have a talk by Namasivayam on the topic of learning to recover from plan execution, errors during robot manipulation, or neuro-symbolic approach. Okay, Namasivayam, you can take over.
Hi. So thanks for the introduction. Robots nowadays, initially robots have been used widely in the industry, but nowadays with the emergence of like foundation models and like transformer based architectures and diffusion based architectures, the robotics is coming slowly to the real world. So industry is trying to basically do household tasks, and they're very good at locomotions and things like that. So when the robots enter human space, so what are the desired properties that the robot should have to basically have a safe interaction with human? First of all, it should be able to understand human intent, what is the concepts that are specified in the instruction and the intent that is specified in the instruction, and it should be able to identify the objects around the world and the state of this world, and it should be able to plan effectively to sequence its action, and then it should be able to execute the actions without errors. Nowadays there's been a surge in doing end-to-end approach for this task. So people either use LLMs or VLMs for this end-to-end planning plus execution, especially VLAs, and there are like other models which are specifically proposed for predicting physics, like world models. So consider this instruction, like construct a, so the question is scaling alone solves the embodied intelligence? Like scaling, it's been observed that scaling alone solve natural language tasks. Is scaling is all we need for embodied intelligence as well? So consider this an instruction of constructing a staircase of height 5 using this white dice. When we ask GPT to actually do this task, it produces a plan which is like this, where the staircase is actually built in the air. So basically this is with GPT 4.1. Of course, there are new models coming nowadays, so some of them has been improved. But even then, if we increase the difficulty of the task and tweak the task a little bit, still they fail in physical feasibility. And this is another example with Cosmos 2.5 Predict, which is a world model by NVIDIA. And the instruction is here to place the blue dice to the right of the red block. And what it does is this. So technically, it so this is what it is seen in the data, and that's hence it is doing that. So it doesn't reason anything about what the blocks are present in the world, and like what is the scale of these objects, and I have to place this object here. But it just whatever it has seen in the data, it is actually doing that. So there's a gap in the inductive and physical reasoning that we can see in these foundation models. So but there is a huge literature where we have where these reasoning and planning has been studied for a long time. Those are like classical symbolic techniques which is available, which can do which can actually predict the precondition and postcondition and reason and plan accordingly. So if we observe the literature, we observe a pattern. So the neural methods are good at handling noises and uncertainty, and they are actually scalable, whereas symbolic methods are data efficient, and they are good at long horizon reasoning and planning. So there is a complementary advantages where between the symbolic and neural world. Now the question is, can we actually combine them? So symbolic representations facilitate long range reasoning and they are interpretable, while neural representations allow generalization and they don't need any hard coded features. They can actually learn that from the data. So there are many ways to combine this symbolic and neural representation. So the hypothesis we took is to induce symbolic prayers, but learn the semantics of those symbols from the data. What do I mean by that? Like I will just explain in a minute. So what inspired us to do that is basically the cognitive modeling of the brain. So there is a theory saying that we have like two systems in our brain. One is system 1 and system 2. System 1 is responsible for reflex tasks like image understanding or something like that, and system 2 is actually responsible for deliberate reasoning. So we thought, okay, why not like use why not combine neural and symbolic systems in that way? So we use neural methods for system 1, which is reflex system, like object understanding and like action execution, etc., and system 2 for reasoning. um, so this is the overall hypothesis of my thesis, but let me come to a particular case where I can explain like how this blending actually helps and how it is useful. So if we consider a class of symbolic neuro-symbolic planners, they usually take a initial image or initial scene as input and a natural language instruction, and output a sequence of action. So, and they use a data set of instruction plus keyframes to train the model. Examples include our own model, which is called in neuro-symbolic robot manipulation framework, and there is a parallel work by Wang et al. Which also does the same, and they actually take initial scene and instruction as input and output a sequence of action to perform the task. But what they assume is the sequence of actions can be executable in the real world. So it's open loop in the sense that they don't track the errors, and they don't track whether the goal is actually achieved or not. And most of the works has been done in simulation, so we don't know what it's this is in 2024, so through 2023, so most of these works has been done in simulation. We don't know whether they would actually perform well in the real world or not. So the first thing we did is to basically do a sim to real transfer. We try to build an autonomy stack. We have a Franca 70 of robot in our lab, and we try to build the autonomy stack from scratch. And we intentionally build the autonomy stack in a modular way so that we can actually test our neuro-symbolic pipeline. So from the environment, we use a RGBD sensor to get the image, and we do object segmentation and create 3D models, and that initializes the world model, which is basically the digital twin of what the environment is. And when the human speak or like dictate the instruction, it goes through a speech recognition model, and we use the hand tracking to identify what actions the human is doing and extract the keyframe accordingly. And this data is used to fine-tune the neuro-symbolic planners, and which produces the sequence of pick and place actions. And once we get the sequence of pick and place actions, we use object tracking to go near the object, and then we use a grass pose estimation model to identify what the grass pose is, and we pick and place the object. So this is an example of our system where we can see we have an RGBD sensor, and it's actually estimating the world. So you can see it's generating detections and segmentations, and it will create a digital twin now. So it has created a digital twin now here. If you can see my cursor, now it's moving to pick the first block, and it's picking the first block, placing it there. The goal here is to actually construct a stack two objects on top of each other. So it's now going to pick the second block, and it will place it there. And the world model is updated accordingly. So you can see the world model will now get updated accordingly. Yeah, so you can see here. So this is a software stack we built, and during the experiments, we observed that actually error happens, and error happens most of the times. For example, it can be a gripper error, a grasping error. For example, it tried to grasp the object, but it didn't grasp. And even if it correctly grasps, it can like fall during the transport, or it can actually place the block little unstably and it can fall down. So all these errors are like happening here. There are other instances of failures where here the yellow block falls down and here the white block is placed unstable. So when we place the next block, the tower is going to collapse. So so the take here is error happens all the time in plan execution. So it can be an adversarial error, like it can be completely displaced, or it can be a small perturbation which would lead the future actions unstable. And it can be constructive also. Maybe the human actually places a block on top of it. So technically human is helping the robot to go near the plan. So the robot should be able to understand these errors and able to recover from them. So for example, now consider this concrete example of constructing a tower using green cube, red Lego, blue dice, and red dice. So an ideal execution should look something like this. So it's placed here, and placed here. So there's a tower actually built here. But an actual execution may look like this. So here the robot actually collides with this tower, and which replaces these blocks. So the future actions that are produced by the neuro-symbolic planner, or like any planner for that sake, would not be executable because the conditions are not met, and hence we need to replan. So the question here is, how would we identify if an error has happened? And even if you identified an error, like how would you localize that error? And once we localize the error, how do we recover from them? So what are the challenges in basically recovering from these plan failures? First, the error detection should be robust to noise in the sensor. Example, the RGB sensor may be like noisy, the depth estimates may be noisy, and like it should adapt to different lighting condition, etc. And it not only able to like detect errors, but it should be able to localize them as well. For example, it's not enough to say some error has happened, but it should be able to say like these are the blocks that has been displaced and this is the error. So during recovery, there are like simple ways to actually recover. So one is to do a repair, immediate repair, which is to go back to the previous state, or just replan from scratch to the goal again. So, but these are like either ineffective or infeasible. I will come to why it will be infeasible or ineffective. And like when original plan is like really long, replanning is like it's really hard, and it's very expensive, error compounds over time. So we should be able to reuse the plan and use the part of the plan as appropriate. Is there any question so far? Okay.
I think we'll take the questions at the end.
Sure. So the problem is, to given a sequence of action, we should be able to detect and recover errors, and the sequence of action is actually coming from a neuro-symbolic planner, which already have a data set of like instruction and keyframes, and we want to technically use the same data set to train the detection and recovery model as well, without having any additional annotation of failures. So that's a problem statement. So what we do, the error detection, so it happens in two steps. One is error detection and then error recovery. So the error detection has three key components. One is state encoder and action encoder, which actually encodes the state into a scene graph. And there is a scene graph predictor, which takes the action embedding and the current scene graph and predict the expected next scene graph. And there is a discriminator, which takes two scene graphs and find the discrepancies between the two scene graphs. So how these I will explain how these three components are combined together to detect the errors. So let's say we have the initial state here, and we have the initial state embedding here. Now, before taking the action A1, we use the scene graph predictor to visualize what is the expected outcome of that action. In actual execution, after actual execution is performed, we compare the state attained with the state that is predicted using the discriminator to identify if some error has happened or not. If an error has happened, then the discriminator will flag that, and it will flag the nodes that are erroneous. So we would be able to localize there. So now coming to the now let's see how these models are actually trained and what's their architecture. So we have the initial, so our data is technically the sequence of keyframes and the plan. So we have action, and this is a scene, and this is the next scene. So we take the object embeddings and the bounding box embeddings and concatenate it to form the embedding for an object. So the embedding would have the object features and the positional features. And we take the node predictor, or the transition model is predicting it node wise. So it takes the action that has to be performed and the embedding of its argument. For example, if it is move top of object 1 comma object 2, then it takes the action ID move top, and it takes the embeddings of object 1 and object 2 that are the arguments, and predict the feature for the object that is to be moved. We use the next scene, and we extract the features from that scene and use that as the and we use MSC supervised loss to train that model. Now the discriminator training, this is the scene graph predictor and state encoder trained together, and this is just straightforward because of we have the supervision. For discriminator, we don't have the supervision. We only have the correct outputs. We don't have the failure states. So what we do is we do a data augmentation of like between two consecutive keyframes. We take the object, the one object would be moved and the other object would be hopefully kept in the same place. So we take the objects that are moved as false labels and the objects that are not moved as true labels. So the discriminator would train to predict the discrepancy in the node features. We use cost entropy loss to train this discriminator, which would predict a score between 0 and 1, depending on how indifferent these two node embeddings are. So we just threshold on like 0.75 to identify errors, and that would tell us the objects that are erroneous. So once we know the error has happened and some objects are erroneous, then we go for recovering from that error. Let's say we have this is the original plan where we have initial state and the goal. At this state ST, there is an error happened and it reaches a erroneous state AC. So what we can do is to go to immediately the ST plus 1 and we can try to do a local repair. But let's say if the agent actually performed a constructive action in the sense that the human or like the external agent actually helped the plan progress. In that scenario, going back to the immediate state is technically undoing the action, the constructive action the external agent has done, and re-performing the action again. So in some cases, like locally doing a local repair is not optimal, and of course, like replanning directly to the goal is costly. So what we do is we take the states and try to have a heuristics of what is the cost of reaching this, how useful will this state be, how useful is this state for the recovery. So we take the cost of going from the erroneous state SC to SK using our discriminator. So let's say if we have n erroneous objects, then this cost would be n, and this we already know from the plan. So what is the length of this, what is the cost of this state. We take the sum of that to have heuristics on how useful this state would be. We rank the states and perform an anytime search to the top k subgoals. So this would allow us to choose the state appropriately. If there is a constructive error that has happened, then the erroneous state will be close to a future state. And if complete kind of, if let's say if there's an adversarial action where the entire structure has been destroyed, then it will be close to the initial state. So it would automatically adjust that accordingly. So we conducted experiments in the simulation environment where we have we introduce different types of error like gripper failure or collision with existing structure or force from a random object, etc. Since there's a lack of time, I would try to like speed it up a little bit. You can see the results in the paper also. So we create a data set of errors in simulation where we have like almost 750 plans, and then we create errors simulated at a random time step, and we can see our model achieves like more recovery rate and it perform the recovery faster than the baseline models. And then we try to finally how scalable is this approach. So we introduce one error at every execution step. The error can compound over time if it is not recovered correctly. So we can see of course there should be a degradation, but our model degrades slowly as compared to the other baselines. So this is a qualitative example. The robot placed it a little bit off, so it tried to correct it, but during that it collided with the tower. Then it tried to recover it and it recovered it successfully. Yeah, it's replaying it. So it can, since there is a positional encoding is also there, so it can recover from small perturbations as well, which is essential for maintaining the stability, especially in case of towers and like stackable objects. You can see that the orientation is like little off. That's one of our limitation of our work. We have to correct that in the future. So let's say, so this is an example where like while local repair is not actually good. So, and adversary has put the yellow red block there, but the local repair actually undo the action and then perform the action again. Whereas the anytime search actually understood that, okay, this is a constructive error, so I should not undo it. And it just went away with action execution. So it's another example where like two more steps are performed by the human and the model identifies, okay, this is constructive error, so it just skips. Yeah. Yeah, thank you for the opportunity. I would be happy to answer any questions.
Thanks, Namasivayam. Questions, please. If you have any questions, please unmute yourself and you can go ahead or raise your hand. Satvik, please go ahead.
Hi. You mentioned that you are encoding the states and there is a state graph. So, could you elaborate on how your state encoding exactly looks like?
Yeah. Since the state is actually a sequence of like some blocks, right? So we use a simple ResNet to extract the object feature for each object. And for position, we take the bounding box and pass it through an MLP to get the feature of the bounding box, and then we concatenate that to form a node feature.
Okay, but the number of objects in any scene could be different, right? So, how do you handle that variability in the number of
That's actually a good question. So we assume that the objects would be the same because let's say you have n objects in the scene and you would be performing. The assumption is the objects don't fall beyond the table. So if it falls beyond the table, then it would be hard to do that. So we assume that, like, we assume the objects are same across the scene.
Okay. But say in two different scenarios, in one you have 4 cubes, in another you have 6 cubes. So will the same model work in both?
Meaning in two different completely initial scenes.
Yes, in one you have to stack 4 blocks, in one you have to.
Yeah, that is completely fine, right? Because in one case we have 6 nodes and another case it would have like 4 nodes. So we use a deduction model to find, like, we use like Dedectron to find how much objects are there. So it would, let's say if 6 objects are there, the assumption is that the 6 objects would be there over the execution of the plan. It would not fall off the table during one plan execution. But if it varies in different scene, then it is fine. Like you have like 4 and then we have 4 nodes and we try to predict those 4 nodes. So the confusion might happen because like the transition function is not actually predicting the entire scene graph at once. It's predicting node by node. So if there are n nodes, we have to call it n times. That's it.
Okay, so the cross entropy loss that you were doing was
Is for the node.
right here.
Everything is for the node.
Node
So
to node.
if I go back. So at every step, there are only few, like every action will not change like every object, right? It will change only few objects.
Yeah.
So that would be there in the argument action. So we predict the next feature for all those objects. We don't predict for the entire scene graph. So it's like a local change that is happening in the scene graph.
Okay. Yeah. Okay. Thank you.
Is it clear?
Yeah, that's clear. Thank you.
Yeah.
Thanks, Satvik. Any other questions from students? Okay, I had a quick question. Like, yeah, I saw the examples for your correction, right? Like, I mean, I kind of understand, like, if you have some kind of like trajectory following, then you want to come back to that trajectory once there's an error.
Yeah, yes.
But here, yeah, at the task level, like, I am kind of still wondering, like, when would it be the cost of coming back to that trajectory and taking that would be better than just going from my current state to the goal state? Like, can you think of an
So
example?
let's say
for
if,
that?
if I understand correctly, the question is like, why do we have to come to an intermediate state? Why not directly plan to the goal? So let's say if the plan is almost like 100 length plan. Let's say if you have to construct a like pyramid of, let's say, size some 20 or 30, where and the error happened at the first step, right? So it is better to come to the third step or fourth step and then just use the remaining trajectory rather than to actually replan everything from the scratch. So let's say if an error if there is an adversary and it keeps on making mistakes at, like, let's say a human actually interrupts at every step, right? Then you would be replanning at every step to the goal, which would be really, really costly.
Okay.
Especially in longer plans.
So here you're trying to reuse the existing plan
As much as possible, yes.
Okay, and you're seeing the closest state that you can go to on that trajectory.
So, exactly. So that's what
this is the figure I was asking.
Yeah. So let's say this is erroneous state. We actually try to patch up with any of the local states. So one option is to patch up with the immediate state st plus 1. That I explained that that's not optimal.
But how would this work? Like if there's dynamics involved in here, right? Like if there's, okay, now you have this initial global plan that you created. So now let's say like the environment is not static.
Okay.
So your initial plan is just a guidance, right? It's not exactly, because some of the states might not be attainable in a dynamic world. Have you thought
So
of that?
so this plan is, yes, it's a guidance, or it's actually the expected sequence of states in an ideal scenario, right?
Yeah.
Let's say if there's no error, if there's an ideal world, so then this should have been attained, this path should have been attained, right? So
No,
the
I'm asking
stochasticity in
like
the environment
this. I agree. I'm asking if you have further, if I add dynamicity in the environment, now do you want to come back to your reusable plan, or do you want to replan? Like which one would be better if there's some dynamicity in the environment? Let's say, so when you have dynamicity, the black path might not be possible, right? Like it might be just a global guidance. I understand, like you're not working on the dynamic environment, but I'm just asking, like how will this be adapted for that?
I'm not able to understand the stochasticity part correctly. So are you saying it's the action uncertainty is there, so expected action may not be attained, or like?
Or states might be changing, right? Like let's say you're doing this pyramid, and then some of the like what you had in example, maybe someone kept 3 of those blocks, or like someone removed 3 blocks, or something happened, or they changed their positions. So your states might not be in the same sequence.
So in an imagined scenario, the state, this is the sequence of state we want to attain, and that would be fixed, right? Let's say if you are to construct a tower, let's come to a simple example, like a tower of height 5. So the states that needs to be the intermediate states that needs to be attained to reach a tower is going to be the same irrespective of whether the environment is unstable, or like whether the environment is stochastic or not. So that is fixed. So that is the ideal states that needs to be reached to construct a tower. Now, because of the stochasticity in the environment, error can happen. So we would be away from the states, but still the states in the trajectory are like they are not exact state, but they are as you told, it's a state that is ideal, right? So you want to achieve to the closest state that is ideal and reuse the plan as appropriate. That's what we try to do. So let's say if the adversary puts 2 blocks on top of each other, so we can the first 4 states have been already achieved, so let's go to the last state. Or like if it can like completely like kind of destroy the tower, then basically we go back to the initial state and like do the plan as appropriate. So, yeah, of course, like we can replan. So that's a kind of like trade-off, but the anytime search actually takes care of that. Let's say in the case goal is actually closest, right? Then we would actually plan to that goal. So
so in your anytime you're anyway filtering out these paths, right? Like so if the cost of coming back to one of these states in the trajectory is higher, then you don't want to go for a replan.
So in that, if goal is actually the state which is closest, then we'd replan to the goal directly.
Cool, thanks. Any other questions? Okay, I think we are also out of time. So let's thank speaker once again, and thanks Namasivayam for taking time and giving us a great talk. It's very interesting, and maybe people can write to you if they have doubts. And I would like to chat with you at some point. Yeah.
Thank you.
Yeah. Cool. Thank you. Thanks all for joining. We'll end the session here. Thank you.